Hi, I'm Bob. Welcome back to the Stata course on regression analysis and estimation methods. In previous videos, we have discussed some essential econometric approaches that alleviate the omitted variable bias. They include the difference in differences, instrumental variables method, and the sample selection corrections. Today, we will explore the panel data models. The panel data structure provides us with a method to eliminate a specific type of omitted variable bias, the time constant omitted variable bias. First, let's take a look at the data structures. There are three main data structures: cross-section, time series, and panel data. The cross-sectional data are collected at a time for many individuals. Each observation is for one individual. The order of observations does not matter because we assume it is a random sample from the underlying population. We do not use the time information in the model. We use the variables attached to each individual in the model. The individual could be a person, a household, a firm, a city, or a country. Here's an example of the cross-sectional data structure. Each observation is for a person, and we have information for each person, including their age, log hourly wage, years of schooling, marital status, race, health, and gender. By contrast, the time series data contains information for only one individual, but over time. The order of observations matters because it represents the trend or pattern of change. Examples of time series data include stock prices, GDP, CPI, and unemployment rate. The third data structure is panel data. It is also called longitudinal data. It can be seen as a combination of cross-sectional and time series data. A panel dataset consists of a time series of each cross-sectional member in the dataset. That is, we observe the same person's variables several times. Let's open the dataset bob4.dta. It contains information on U.S. workers participating in the panel study of income dynamics, PSID surveys. We type browse and find each worker's ID, the year of the survey, age, years of schooling completed, region, union membership, gender, and wage. The data are arranged so that the same individual appears multiple times in different years, and then the next individual. Such an arrangement is called the long form of panel data. The data must be in the long form when we use data as commands for panel data. We can always find the individual identification variable and the time variable. They are the basic unit of the panel data. In our example, the individual identification variable is the ID variable, and the time variable is the year variable. We use the xtset command to declare the data to be panel data before we use other panel data commands. We type xtset followed by the individual identification variable ID and the time variable year. We can take advantage of the panel data structure to alleviate. The idea starts with the decomposition of the error term. we first write down the panel data model. Keep in mind that there were two dimensions of panel data, the individual and the time. Therefore, we use the subscript I to represent the individual and t to represent time for each variable. We decompose the error term epsilon it into two components, ai and mu it. The ai component captures all unobserved time constant factors that affect the outcome variable y. This component of the error term has no t subscript. It does not change over time. It differs among individuals. It is called the individual fixed effect or the individual heterogeneity. The second error term component, mu it, is called the idiosyncratic error. It represents unobserved factors that change over time and differ across individuals. That is why it has both the I and T subscripts. The overall error term epsilon it can be written as the sum of the individual fixed effect ai and the idiosyncratic error mu it. Epsilon it is often called the composite error. The individual fixed effect ai contains all factors that do not change over time but affect the outcome y. In our example, they include the worker's gender, years of schooling completed, and other time constant characteristics of the workers. The panel data method aims to take into account the time constant unobserved factors in AI as if we have controlled them in the model. The trick is that we include them in the model, but we don't need to estimate their coefficients because we can find a way to eliminate them from the model. By doing so, the estimates of the variables we are interested in are the same as if the unobserved factors are held constant in the model. There were four main panel data methods to estimate the coefficients consistently, even if the unobserved error component ai is correlated with the explanatory variable x. The first one is called the time-demeaning fixed effects transformation. We consider a model with a single explanatory variable. For each individual I, averaging the equation over time gives the within averaged equation. Because ai is constant over time within each individual, it remains the same in the within averaged equation. We subtract it from the original equation and obtain the time-demeaned equation. The resulting data are called the time-demeaned data because they come from the subtracting of the individual's mean over time. The time-demeaning fixed effects transformation is also called the within transformation because the method uses the variation in y and x within each individual to estimate the coefficients. Notice that the individual fixed effect ai has been removed from the model during the transformation. However, the coefficient beta 1 we are interested in remains in the time-demeaned equation. We use the OLS method for the time-demeaned equation, and the estimator beta 1 hat is called the time-demeaned fixed effects estimator or the within estimator. The time-demeaned fixed effects estimator is a consistent estimator as long as x is not correlated with the idiosyncratic error component mu. The most important thing here is that the explanatory variable x is allowed to be correlated with the unobserved factors that are constant over time in AI. In other words, the fixed effect transformation alleviates the bias due to the time constant omitted variables. We don't need to worry that some variables are unmeasured or unobserved as long as they are constant over time, such as gender, educational attainment, race, and some innate ability and personality. The AI has been eliminated during the time-demeaning transformation, so we don't need to estimate it. This is the most commonly used panel data method, and it is the main panel data estimation method in Stata. The second panel data method is called first differencing. We can write down the equation in time t-1. Then we subtract it from the equation in time t and obtain the first differenced equation. We find that the individual fixed effect AI has been differenced away. The coefficient we are interested in, beta 1, maintains in the first differenced equation. We can use the OLS method to estimate the first differenced equation and obtain a consistent estimate of beta 1 as long as delta x is not correlated with delta mu. As in the within transformation, the unobserved error component that is constant over time is allowed to be correlated with the explanatory variable x, and the coefficient estimate is still consistent. It also solved the omitted variable bias problem due to the time constant factors. The third method is the fixed effect dummy variable method. It adds dummy variables to the model to capture the fixed effects. For I individuals, we add I-1 dummy variables to the model, and they will be estimated along with the betas. It is not practical for a large number of individuals, but it works well to capture the time fixed effects. We usually include the year dummy variables in the model to control for the time fixed effects. With the fixed effects dummy variable method, each individual's time constant factors are in the fixed effects dummy, and we estimate them directly. The above three methods are the traditional approaches for panel data. These methods have a drawback. We cannot estimate time constant variables because they will be also removed from the model during the transformation. The fourth panel data method overcomes this disadvantage and is increasingly used in research. It is called correlated. Including the within average variables means to hold the individual average fixed. It's equivalent to the fixed effect within estimator because we hold the within average fixed and use the within variation to estimate the coefficients. The idea of the correlated random effects approach is that because the individual fixed effects error component AI does not change over time, we assume that it is correlated with the average level of the explanatory variable x. Suppose AI relates to the average level of x in a simple linear relationship. Substituting this linear relationship to the original equation gives an equation that contains the average level of x. The error term nu I and mu it do not correlate with x now, and we can use the random effects method to estimate beta 1. The estimator beta 1 hat is consistent as a result. This method allows the unobserved factors AI to be correlated with the explanatory variable x, And the name of this method comes from the fact that we substitute the correlation expression in the original model. The advantage of the correlated random effect approach is that we can estimate the time constant variables in the model. We have learned 4 methods to estimate the panel data models. They decompose the error term into 2 components and find ways to estimate the coefficients consistently, even if the explanatory variable x is correlated with the individual fixed effect error component, AI. The unobserved factors that do not change over time, such as innate ability, race, gender, birthplace, and some family background. These methods take advantage of the panel data structure of the error term and adjust the bias caused by the time constant omitted variables. We can call all these 4 methods the panel data fixed effects methods. They differ from the other 2 methods, the pooled OLS and the random effects. We can apply the OLS method to panel data without considering the structure of the error term. Such a method is called the pooled OLS. However, unlike the fixed effects methods, the time constant error component is not allowed to be correlated with the explanatory variables if we want to get consistent estimates using the pooled OLS. Another method does consider the structure of the error term and decomposes the error term into 2 components like the fixed effects methods, but it assumes that the composite error term, including both the time constant and the idiosyncratic error components, are uncorrelated with the explanatory variable x. Then, there's no need to use the fixed effects methods to eliminate the time constant error component AI. The structure of the composite error term leads to a positive serial correlation. The random effects estimator takes into account such correlation, and therefore the standard errors are correctly computed. The random effects estimator is a feasible GLS estimator. It assumes the error term is not correlated with the explanatory variables as the pooled OLS, but it differs from the OLS in constructing the error term in the model. Next, I will show you how to do pooled OLS, random effects, and the 4 fixed effects estimation in Stata. We use the panel dataset BOB4.dta for the US workers. It contains wage, union status, gender, age, educational attainment, and other information for US workers between 25 and 54 years of age. Suppose we are interested in the relationship between wages and the workers' union membership. Let's first fit the pooled OLS regression. We type regress log wage union. We execute it and find that union members earn around 3.6% more than non-union members on average. Second, let's run the random effects model using the xtreg command and the random effects option. We type xtreg log wage union and the option RE. We see that union members earn 3.7% more than non-union members. Third, we employ the time-demeaning fixed effects method using the FE option. The fixed effects estimate is slightly higher than the random effects estimate. Fourth, we estimate the panel data model with the first differencing method. We can do it manually. We generate the first difference variable using the by sort prefix. For each worker, we generate the first difference outcome variable and explanatory variable. Then we regress the first difference log wage on the first difference union. And the OLS estimate is the first difference estimate for the original model. The estimate is 5.6%. Fifth, we use the dummy variable method. We include the dummy variable for each individual by adding i.id to the model. It takes time to estimate with so many dummy variables, and the estimate for the union is 3.7%. 6. To find the correlated random effects estimate, we add the within average level of the explanatory variable to the model and then adopt the random effects method. The within average is computed using the by sort prefix. We type by sort id, followed by the xtreg command and the mean function. Please check out my Stata tutorials on those Stata commands. We add the within average to the random effects model and obtain the correlated random effects estimate, which is 3.7%. We usually add more control variables to the model. In the pooled OLS, we add age, years of schooling, gender, and year dummies. The year dummies capture the time fixed effects. We also add these controls to the random effects model, the fixed effects model, and the correlated random effects model. We compare the estimates in a table using the stab command. The time-demeaning fixed effects and the correlated random effects estimates for the union variable are identical. The time constant variables will be dropped automatically in the fixed effects model. However, they can be estimated in the correlated random effects model. Thank you so much for watching this video. See you soon on the next topic. Goodbye. Thank you for watching this video and subscribing to my YouTube channel. See you next time.